Hey, what's up everybody, and welcome to another section of this Algorithmic Patterns course focused on the BFS pattern. In this section, we're going to go over our second problem using the BFS pattern, which can be found by filtering the Leetcode patterns list like so. In this problem, given the root of a binary tree, we're asked to return the average value of all nodes on each level. That is, for each level of our tree, we want to get the sum of all of the node values and divide that sum by the number of values or nodes for that level. And that's just because to calculate the average for a group of numbers, you just divide the sum of all of those numbers by the number of numbers. To solve this problem, we're going to traverse our tree in a breadth-first or level order manner, calculating the average at each level and appending the average to an array. The important thing to notice here is the pattern being used throughout these problems. We're always using the queue data structure to traverse these trees in a breadth-first manner. The reason for going over multiple problems which use the same algorithmic pattern is to solidify the concept in your mind and to help you to understand that a single pattern can be very powerful in that it can be used for multiple different problems. So being able to identify problems where you can apply specific patterns is going to be one of the ways that you will be able to level up your ability to solve these types of problems. So with that in mind, let's get into writing some code. Okay, so within our Python source coding interview patterns directory, we will just change directory into our BFS directory. And within this directory, we're going to create another directory that we're going to call average of levels in binary tree. And we'll just change directory into that directory. And in that directory, we will create a file called average of levels in binary tree.py. And similar to the last problem, we're going to import the module called collections so that we can use its deck data structure. And we're also going to need to get the tree node class from our problem. So in the problem description, we'll just go to Python 3 for the code section, and we'll just copy this class. And then we can just go ahead and paste that class into our code and uncomment out the class. And this code is going to be very similar to our last problem's code. So we're going to go ahead and start with our entry point. So if name equals main. So here we're going to need to create our binary tree. So the binary tree in the problem description is actually the same binary tree from our last problem as well. So its root node is 3, and this node contains 2 child nodes, 9 and 20, and 9 has no children, and 20 has 2 children as well. So we can just set BT for binary tree equal to tree node, and this is going to be our root node, which is going to have a value of 3, and it's also going to contain 2 more tree nodes as its left and right node. And remember, our root node's left node has a value of 9 with no children. So for this left node, we can put 9 and none for both children. And for this root node's right node, it has a value of 20, and this node has 2 children. So we'll put 20 for the value, and we need to add tree node for 2 more children. And both of these children have no children, so we're just going to do this node's left node with a value of 15 and this node's right node with a value of 7, and both of them will have none for both children. So that's going to look something like this. So now we have our binary tree, so we can just go ahead and pass the binary tree into our function that's going to contain our algorithm. So we're just going to print the result of a function called average of levels, and that function is going to take in our binary tree. And now we need to create that function, so we can go here and just define average of levels. and it's going to take in a binary tree or a root node, let's say. And just like for the last problem, we're going to create a queue because the queue is necessary to do level order or breadth first traversal. And we're going to use the deck data structure to create our queue. And then we're going to create a list that we'll call AL for averages list. And we're just going to create the empty list. And to start, we want to append our first node or the root node to our queue. And following that, we will start our while loop. So while length of queue. So while our queue still has items or nodes within it, then we will continue to iterate through the while loop. But once there are no more items in our queue, we will terminate the while loop. And let's just go down here. And we're going to start by creating a variable for our sum values. So this is going to be the sum of all of the values for our level, because we need to calculate the average for the values of each level. So for example, if we're on this second level here, we need to calculate the average of 9 and 20. And to get the average of a list of values, we just get the sum of all of the values and divide them by the number of values. So sum val is going to be the sum of the values on each level. Then we're going to create size, which equals the length of queue. And the size is going to be the size of the current level. And we need to get the size at this point because once we start popping nodes off of the queue, we'll no longer have a way to determine the level's size. So we'll set our size equal to the length of queue at this point, and we're going to iterate through the size. And for each iteration of size, we're going to set our node equal to queue.popLeft. So we're going to take the leftmost value of the queue because a queue is first in, first out. So the leftmost value is going to be the first value that was inserted into the queue. And we're going to add its value to our sum vals. And then we're going to check to see if that popped node has children. So we'll start with if node.left. And if there is a left child, we're going to append that child to the queue. So we're going to add it to the end of the queue. And we're going to do the same thing for the right child. So if node.right, we're going to append to the queue node.right. And then after, we're going to exit the for loop. And once we've calculated the sum for and added the children of the nodes for the current level to our queue, we'll go ahead and add the average of that level's values to our averages list. So sum vals divided by size. So size is the number of nodes in the level, and sum vals is the sum of all values for all of the nodes of the level, which will result in our average. And we're going to do that for each level, and then once we've done that for each level, we're just going to return our averages list. And that's going to be it for this algorithm. It's actually very similar to the previous problem's algorithm. The only thing that we're really changing here is instead of just adding each node of the level to an array, we're just calculating the average for the nodes of the level. So let's go ahead and save this and test. So if we look here, the expected output is here. They're expecting 3.0, 14.5, and 11.0 as the output, as the list of averages that are expected to be returned. So when we run this, that's what we should expect as well. And we get 3.0, 14.5, and 11.0 as our output as expected. Now let's get into the visualization of this algorithm. Okay, so let's go ahead and attempt to visualize this code. So we can just start by drawing out our binary tree here. So we'll start with a node, and actually let's use white. So just erase that. So we'll start with a root node, and its left node and right node. And this node will also have a left node and right node. And this node here won't have any children. And the data will be 3 for this root node, 9 for this left node, 20 for the root node's right node, and 15 and 7. So this tree, or this root node, is going to get passed into our average of levels function. So we're just going to pass this into the function here as the argument. And we're going to start off with an empty queue and an empty averages list. So let's go ahead and write both of those out as well. So our queue is going to be empty in the beginning, and our averages list is going to be empty as well. And maybe this will be a little bit longer. And to start, we're just going to append the root to our queue. So this value here, we're going to append to our queue. So we're going to add the value 3 here. So we'll go ahead and put a 3 there. And then we're going to start our while loop. So our while loop is going to iterate while the length of our queue is not 0. So currently the length of our queue is 1. We have 1 item in our queue, so of course we'll do the code here. And we're going to start with our sum values equaling 0. And we're going to start with our size being equal to the length of the queue. So this part of the code here is very important because we need to keep track of the size so that we're only calculating the average for the nodes within a given level. So for this first iteration of the while loop, we're on this first level here. So we only want to get the average for this node. We don't want to get the average for any other node in this tree. So we need to essentially take a snapshot of the size for the level, which is the number of nodes for the given level, or for the level that we're on. And we need to do that now because once we start iterating through the size for the level, we're going to start to actually pop items off of the queue. And of course, we wouldn't have any way to know when to stop iterating this for loop here if we didn't have a size in the beginning, because this for loop is going to do work on each node within a level. So for this first level here, we're going to set our size equal to the length of queue, which is 1. There's only 1 item because there's only 1 node in this level. So right now our size is going to equal 1. And we're going to iterate through the range size because we want to do this code on every node for the given level or the current level. So size is 1, so we're going to iterate 1 time. And for this first iteration, we're going to set our node equal to the node that's currently in our queue. So we're going to pop this node off of our queue. Queue.pop actually removes this from our queue. So we're going to pop it off, and we'll just write it out here so we know that this is the one that we're working with for node. So we popped it off of the queue, and now our node is set to this node, which is this node. And then we're going to add to our sum values the value 3. And here, this node.value, remember our node data structure looks like this. We have something like class node, and node has a value, a left, and a right. Roughly, this is what our node class looks like. So node.value is going to be the value in the node, and node.left is going to be its left node, and node.right is going to be the node's right node. So here we're adding the value to our sum. So we're adding 3 to the sum. So our sum, we just do plus 3, which equals 3. And then we're going to check if our node has a left node. So does this node have a left node? Yes, it does. And if it does, we're going to add it to the queue or append it to the queue. So we're going to add this 9 to the queue. And then we'll go here and check to see if our node has a right node. So does this node have a right node? Yes, it does. So we're going to append the right node's value to the queue as well, which is 20. And then this is where we're going to actually append our average for this level. This level here, we're going to append this average to our averages list. The average for this one node here is of course going to be 3. The sum of our values is 3, and 3 divided by 1 is 3. So here we can just go ahead and add 3.0. And then we'll head back to the top of our while loop here. And our queue still has items in it. We have 2 items. So we have 9 and 20, these 2 nodes. So we're still going to do this code here, and we're going to start with sum vals, setting it equal to 0 once again. So we can just erase this, and we can erase that. And once again, our size is going to be the length of the queue, which is going to be 1, 2, because we put these 2 items in the queue. So now we're working with this level because these 2 items are in the queue. So our size is going to be 2. And then once again, we're going to iterate 2 iterations this time. We're going to iterate through the size. And we're going to first pop the first item that was added to the queue off of our queue. So we'll pop left. So we're going to pop this 9 off. So we'll just pop that off. So now we're dealing with the 9 here. So now we're handling this node here. And we're going to add this node's value, which is 9, to our sum values. So sum values plus 9 equals 9. And then we're going to check if this node has a left node. Does it have a left node? No. So we're not going to do anything here. And then we're going to check and see if it has a right node. Does this node have a right node? No, it does not. So we won't do anything here either. And then this time, since our size is 2, we're going to go back to the top of this for loop. And we're going to do one more iteration, our second iteration, because the size is 2. And once again, we're going to pop another node off of our queue. So we're done with this 9. Now we're going to pop this 20 off of the queue. So now we're handling this 20 here. So our node is set to 20 now. And we're going to add to our sum values this node's value, which is 20. So we'll add 20 to 9 here. And that just equals 29. And then we'll check to see if this node has a left node. So 20 does have a left node, so we're going to append that to the queue. So we'll append 15 to the queue. And then we'll check to see if this node has a right node. So 20 has a right node, so we're going to append this node to the queue as well, 7. So we'll append 7. And after we finish this code here, we're finished with this for loop because we're only iterating through the size 2. So then we'll end up here where once again we will append the average for this level to our averages list. So our sum values now is 29 and our size is 2. So 29 divided by 2 is 14.5. So to our averages list, we put 14.5. And we are done with this 20. And once again, we end up back to the top of our while loop here. And our sum values gets reset to 0. So we can erase all of this. And our size gets reset to the length of queue. And the length of queue is 2 once again. So we'll just leave this here. And then once again, we're going to iterate through our size. So for blank in range size, which is 2. So now we're going to pop left again. So we'll pop this 15 off. And then we're going to add this 15 to our sum vals. So sum vals plus 15 equals 15. And then we're going to check to see if this node has a left node. Does 15 have a left node? No, so we won't do this. Then we'll check to see if this node has a right node. Does 15 have a right node? No, so we won't do this. And then we're going to go back up to the top of the for loop again, because we have one more item in size. And we're done with 15. And now we're going to pop left once again. This time we'll pop this 7 off of our queue. So now we're dealing with this 7. And then we're going to add the value for this node to our sum vals. So add 7 to 15. So plus 7 equals 22. And we'll check to see if this node has a left node. So does 7 have a left node? No, so we won't do this. And does 7 have a right node? No, so we won't do this. And we're done with this for loop, and we're going to end up here, where we're going to append to our averages list 7 divided by 2, which is going to be 11. So we'll put here 11.0. And at this point, we get to the top of our while loop again, but this while loop is only going to continue while the length of our queue is not 0. But currently our queue is empty. So this while loop would not continue at this point. So now we're going to go down here and just return our averages list. So we'll return this list here, which is going to have 3.0, 14.5, and 11. And that is how this code is working and how we can visualize it. So now let's go ahead and get into time and space complexity. So we can go ahead and just erase this stuff to make some space. So for our time complexity, as you saw, we had to touch every node in this tree because at some point we had to add every one of these nodes to our queue. So that means that our time complexity is big O of n, where n equals the size of tree. So our input is the tree, and our algorithm needs to touch every element in this tree. So as this tree gets larger, the time complexity of our algorithm will scale linearly with the size of the tree. And it's pretty straightforward. And as for our space complexity, Our space complexity is going to be a little bit more complicated, being O of n minus 1, where in the worst case, if we had a tree that looked something like this, where we had a level here and we had one more level here, in the worst case, we would need to store this entire level here in our queue. So in the worst case, we would need to have 9 and 20 in our queue. And let's just remove this too, just to prevent confusion. So in the worst case, we would need to have both these nodes in our queue. And the size of our n is 3 in this case. But we wouldn't need to have both of these levels in our queue at the same time. At the most, we would need to have this larger level in our queue in the worst case. So if our n here is 1, 2, 3, but in the worst case, we only need to have this level, 1, 2, then for this case in particular, O of 3 minus 1, because our tree size here is 3, but we're only needing to add this level, so 3 minus this top level, and this would simplify to O of 2. So in the worst case, we would need to store O of n minus 1 nodes in our queue. In big O, we ignore constants, so we don't need to think about this -1 or this -1. So our space complexity is actually equal to O of n as well. And for our space complexity, let's also consider one more example. So we can go ahead and erase this. And let's assume for a second that we have a tree that looks like this. And we'll just throw some random values in here. And let's remove these from our queue. So this final level of the tree here is going to be the level at which our queue holds the most nodes. So at this level here, our queue is going to need to hold 2, 3, 6, and 4. So that's 1, 2, 3, 4 items. And the size of our n is 1, 2, 3, 4, 5, 6, 7 items. So this level contains roughly half of the size of our n. So in that case, our space complexity would look something like O of n divided by 2. Since at this level we're holding roughly half of our whole tree. So roughly, for a tree that looks like this, our space complexity would look like this, O of n divided by 2. But once again, we're going to ignore the constant, which would again make this just O of n. So here's another situation where in the worst case, our space complexity, or the number of nodes that our queue needs to hold, is O of n. And I hope that makes sense. So that's going to be it for this section and for this problem, and I will see you in the next one.